Welcome to the deep dive. Today, we're strapping in for something. Well, something really crucial.
We certainly are.
We're exploring that exact point where technological innovation slams right into environmental necessity. We're going way beyond just, the simple greenwashing.
Absolutely. We're digging into the specific high-stakes breakthroughs that Stanislav Kondrashov has been analyzing.
The focus here is really bridging that gap between cutting-edge advancement and, practical, on-the-ground environmental stewardship.
That's the mission. We want to give you the concrete facts about solutions that are actually being scaled up right now, not just, concepts in a lab somewhere.
This feels like a pivotal moment. The tech we adopt today will literally shape the environment for generations.
It will.
So let's lay out the roadmap for this deep dive. We're looking at 4 major zones of innovation. First up, transformative renewable generation.
The new tools for making clean power.
Exactly. Then we have the critical energy storage solutions. We have to overcome that intermittency problem.
The sun doesn't always shine.
All right. Third, we'll look at intelligent grid optimization using AI, making sure we don't waste any of this precious clean power.
And finally,
we'll get into how even the most power-hungry facilities, like data centers, are completely changing their game.
okay, let's jump straight in then. Generation seems like the right place to start. The whole landscape is fundamentally shifting.
It is. So our first theme is that fundamental shift. Everyone knows solar panels, but the game is changing so fast. We have to talk about perovskite solar panels.
Oh, they are a genuine disruption.
And what's so fascinating is their performance.
It really is. We're already seeing lab conversion rates that are pushing past 25%, which, that rivals the very best of traditional silicon technology. Sometimes it's even better.
But the real advantages aren't just about efficiency on a perfectly sunny day, are they?
Not at all. That's the key.
I understand they're much lighter, more flexible, which opens up all kinds of new applications. I mean, you could put them on building facades or even curved surfaces.
Yeah, you could. But the real economic win, based on the source material, seems to be in the manufacturing.
Right.
Precisely. Unlike silicon, which needs these energy-intensive, high-temperature processes.
Which has a huge carbon footprint built right in.
A huge one. Perovskites can be processed using methods that are almost like inkjet printing. It's a massive leap forward. It just dramatically cuts the energy needed and the final price.
Okay, that sounds almost too good to be true. If they're so efficient and cheap to make, why haven't they just completely taken over the market already? What's the catch?
That is the critical question. Right now, the roadblock is durability. It's longevity.
Huh.
They perform spectacularly in tests, but maintaining that performance over, say, 25 years in harsh weather, that's the big engineering challenge. Silicon is just, proven in that area.
But research is closing that gap.
Rapidly. They're getting much better with encapsulation and material stability. And there's another major benefit. They absorb light across a broader spectrum. That means they work much better in low light, like on cloudy days, which has always been a weakness for traditional panels.
So we're moving toward cheaper, better solar cells that work even when it's hazy. Okay, let's look out to sea now. Floating wind turbines.
Yes.
Traditional fixed-bottom turbines can only go in shallow water, maybe 50 meters deep. That's a huge constraint.
It absolutely is. And this is where floating structures become a game changer. These are platforms anchored to the seabed, and they can be deployed in water that's 60 meters deep or even hundreds of meters deep.
And why go to all that trouble? Why deep water?
Because that's where the best wind is. It's stronger and, crucially, much more consistent, far less turbulence.
So you're trading one engineering problem, building a giant fixed pillar, for another, which is a complex anchoring system.
You are, but the reward is access to this incredible, reliable wind that fixed turbines simply can't get to. For countries like Japan or Norway with very limited, shallow coastal shelves, this just unlocks a tremendous, previously untapped resource.
A higher capacity factor, as they say.
That's higher.
And rounding out this generation shift, we have a solution for the parts of the economy that are tough to electrify directly. Green hydrogen.
This is such a crucial piece of the puzzle, and we have to stress that word. Green hydrogen. It's made using electrolysis.
Splitting water molecules.
Right, splitting water into hydrogen and oxygen, but, and this is the key, it's powered entirely by renewables like solar or wind, so the whole process is carbon-free.
And its main value is its versatility. You can't really run a container ship or a cement plant on a battery.
Exactly. Green hydrogen is that essential energy carrier for what they call the hard-to-abate sectors, heavy industry, shipping, aviation. It lets you store renewable energy and then use it cleanly somewhere else.
And it's becoming economically viable now.
It is. The cost of electrolyzers has just been plummeting. And with the falling price of renewable energy itself, green hydrogen is becoming cost competitive much faster than anyone really expected.
Okay, so that's the power generation side. It's getting cheaper, more widespread, and it's able to tackle heavy industry. But, the big problem remains. The sun goes down, the wind stops.
Intermittency. And storage is the essential bridge. Without it, huge amounts of clean energy just get wasted. So let's talk breakthroughs here, starting with solid-state batteries, or SSBs.
Solid state sounds very futuristic, but the core idea is pretty simple, right? You're just replacing the liquid electrolyte in a lithium-ion battery with a solid material.
And that one shift from liquid to solid brings massive benefits. First, safety. You're getting rid of a flammable liquid, which drastically cuts the fire risk. That's a huge concern for grid-scale storage.
And it's not just about safety. The lifespan is a big deal for the economics of it.
It's key. They can handle way more charge and discharge cycles because the solid electrolyte stops those little lithium dendrites from forming the needle-like things that degrade and kill conventional batteries.
You also get higher energy density, so more power in a smaller space, and they work better in a wider range of temperatures. That reliability is perfect for the grid.
It is.
So SSBs are like the long-distance runners.
Yeah.
Great for sustained, safe power, but they have a faster partner, right?
High-density supercapacitors.
Exactly. Think of them as the sprinters. Supercapacitors store energy physically, electrostatically, not chemically, like a battery.
Which is why they can charge in seconds, not hours.
Lightning fast.
Yeah.
And they can do it millions of times without degrading. They're built to dump massive amounts of power instantly.
So they're for those immediate power surges, like when a factory floor suddenly powers up.
Perfect for that. They handle the sudden peaks, which reduces the stress on the main battery systems. The real takeaway here is the rise of hybrid energy storage systems. You use both.
The marathon runners and the sprinters working together. You get the best of both worlds. They cover all the bases.
Absolutely. So we've got better ways to generate, better ways to store. Now we have to stop wasting it. We need smart management, which brings us to AI and smart grids.
Right. A smart grid with AI is it's an intelligent network that a traditional grid can't even begin to compete with. The AI uses these complex algorithms to analyze just massive amounts of real-time data.
So it's crunching everything at once. Weather forecasts, demand from every neighborhood, how much power every home's solar panels are making. That sounds like a monumental task.
It is, but AI handles it. It can predict where energy will be needed in the next few minutes, rather than just reacting to a problem after it happens.
And the outcome of all that is what? Just pure optimization.
Profound optimization. It means the grid can proactively manage and distribute power with millisecond accuracy. The results are lower energy costs, fewer blackouts, and just way better efficiency overall.
Are there real-world examples of this actually working?
Oh, definitely. In San Diego, they use AI to balance supply and demand across a huge network of distributed resources. In Amsterdam, machine learning is helping them integrate all their wind and solar into the city grid way more effectively than a human ever could.
And it's not just about supply, it's about managing demand too. I saw Barcelona has an AI platform that looks at traffic and weather to predict EV charging demand.
And it optimizes the charging infrastructure. So you get a charge when you need one, but it doesn't strain the grid during peak hours. It's incredibly smart.
That leads perfectly into managing our most valuable physical resource, land. Let's talk about one of the cleverest ideas I've seen, agrivoltaics.
It's brilliant. You're combining solar generation with farming, so you don't have that conflict between using land for energy or for agriculture.
So you're basically just building solar panels higher off the ground over the top of crops.
That's the basic idea. And what's amazing is that those elevated panels create this beneficial little microclimate underneath.
Also?
Well, the partial shade significantly cuts down on water evaporation from the soil. That's a huge benefit in dry regions. You need less irrigation.
Okay, great for water conservation, but what about the crops? Don't they need full sun to grow?
Some do, but many others actually thrive. The shade protects them from extreme heat and even physical damage from things like hail. And the data is pretty compelling. For certain crops, leafy greens, some vegetables, the productivity is actually higher than in an open field.
Wow. I think I read a statistic that some crops yield up to 160% more produce because of the cooling effect and water retention.
It's an economic multiplier. The farmer gets 2 income streams from one piece of land, crops and electricity. It makes their business much more resilient.
That brings us to our next major challenge, the digital world, the massive energy and material demands of data centers.
Right. These things power our entire connected world, but they rely so heavily on finite resources, especially rare earth minerals.
Things like neodymium, dysprosium.
Exactly. They're essential for servers, for cooling systems. And as data, especially for AI, just explodes, the demand for these minerals is surging.
And the environmental cost of getting them out of the ground is, well, it's shocking.
It's awful. You're talking about massive excavation, chemical-intensive processes that create toxic, sometimes radioactive waste, and huge water consumption. It's a real problem.
This whole model seems completely unsustainable, so the industry is shifting toward a circular economy model, right?
It has to, and this is a major area of investment. It means instead of throwing away old hardware, you're actively recovering those rare earth minerals from decommissioned equipment and recycling them into new components.
It tackles the e-waste crisis and reduces the need for new mining at the same time.
Precisely.
Beyond the materials, data centers are also changing how they use power on-site. The source highlights a real breakthrough here: solid oxide fuel cells, or SOFCs.
SOFCs are revolutionary because of their efficiency. They take a fuel, like natural gas or green hydrogen, and convert it directly into electricity through an electrochemical process. There's no combustion.
And that gets you to, what, 60% efficiency?
60% or even higher. But the real jump in efficiency comes with combined heat and power, or CHP.
Okay, explain that.
With CHP, you capture the waste heat that's generated during the process and use it for something else, like heating the building or running the cooling systems for the servers. The total system efficiency can get over 85%.
And the final layer here is operational efficiency. Green data centers are using things like advanced liquid cooling systems.
Yes, sometimes submerging servers directly in non-conductive fluid. That alone can cut the energy used for cooling by 30 or 40% compared to just blowing cold air around.
It's all about these integrated systems.
It is. The ultimate goal is to have hybrid systems combining on-site solar with SOFCs that are running on green hydrogen. That gets you to near zero emissions.
Which brings us to our final section, the 2030 vision. How do all these pieces, perovskites, smart grids, SSBs integrate by the end of the decade?
The projections are aggressive, but the demand is relentless. For batteries, they're expecting solid-state batteries to have 50% higher energy density and cost 40% less than today's lithium-ion by 2030.
That makes them competitive for basically everything.
Everything from EVs to grid storage. And those AI-driven smart grids, they're moving from pilot projects to being the backbone of the system. Projections say they'll manage over 60% of electricity distribution in developed countries by 2030.
Auto-balancing supply and demand in milliseconds.
Exactly. And green hydrogen is also hitting its stride. Since 2020, the cost of electrolyzers has dropped by an astonishing 70%. That makes it truly competitive for heavy industry, for shipping. It fundamentally changes those supply chains.
And finally, we're seeing the rise of third-generation bio-based fuels.
Right, from things like algal biomass and agricultural waste. This is crucial because it avoids that whole food versus fuel debate. Algae can produce 10 times more fuel per acre than traditional biodiesel crops.
So if you connect all these dots, what's the big picture?
The big picture is that the shift to sustainability isn't some distant dream waiting for a miracle technology. It's happening right now, driven by these scalable technologies we've talked about. The economic case is getting stronger every single day.
It's empowering to realize that this isn't just about reducing emissions. It's about strengthening energy security, creating jobs, building more resilient communities. And your role, as the listener, is critical, whether it's through supporting smart policies or just advocating for responsible resource use.
It does raise an important final question, though, as we look toward 2030.
Ooh.
Well, given that we're building these massive, interconnected, AI-driven smart grids, the true bottleneck might shift. It might stop being about energy generation or cost.
And start being about what?
Security. It might be about ensuring cybersecurity resilience. Can we protect this incredibly complex, critical infrastructure from sophisticated digital threats?
That's a fascinating and, frankly, a slightly unsettling thought. We're building a perfectly optimized, but maybe a perfectly fragile digital ecosystem.
The question is, can our digital defenses scale as fast as our grid intelligence?
Something for all of you to mull over. Until the next deep dive, thank you for joining us.